Good morning, and it's great to be here at the Haskell Symposium this morning. Thanks for coming in so early after a great first day. So this work is work that I've actually been working on for about a decade, first in the context of the Zen project, and then later on as an academic at the University of Cambridge. So while I'm presenting this, obviously in a personal capacity, it represents the work of a cast of over 100 people now. So as we go along, I will credit people as appropriate. Now the slide decks I'm showing you here are actually self-hosted in the operating system that I'm going to describe, and several URLs are embedded in the presentation. So if you feel like following along, and you can get the TCP stack to work, then dex.openmirage.org/Haskell 2014 has all of the content. But let me just dive straight into it first. So as a long-time systems programmer, I'm not really a functional programmer by training. Quite often we discover that it's very, very hard to build conversational systems in real life. And this particularly came up in Twitter recently. Marius Eriksson gave a great talk at CFP a few years ago and also at SOSP, describing how difficult it is to build composable software elements in order to build reliable systems such as Twitter's backend servers. And so a large part of the work that I'm doing is trying to build a nice kind of compositional property to the systems that we construct by leveraging versions of functional programming. And so why is this? The reason is just sheer complexity. So we saw this in Kathleen Fisher's great keynote at ICFP, that our systems have become so complicated and so intertwined that it's just almost impossible to disentangle our application logic from the low-level grungy details of what happens inside systems APIs for various reasons, such as performance requirements or keeping down memory usage or whatever that is, or quite often because of legacy reasons. Now, just 10 years ago, I would have been tweaking a physical machine with just the right software installation in order to prepare this talk. This might have been a Windows machine. I would have made sure it had just the right set of users, the right set of profiles. And these days, modern operating systems still are highly dynamic, highly multi-user systems. In reality, though, we don't need such a level of dynamicity when we're deploying services in the cloud. General-purpose operating systems that force generality on all of the things that all of the situations they're deployed in can actually be very, very harmful because they provide a whole bunch of functionality that we don't need in many, many situations. And in addition to just providing too many features, just the sheer amount of interaction between these components becomes absolutely insane. So if you have ever configured a Linux box in recent times, you have a huge amount of choice in terms of distribution, in terms of versions. A lot of it is because of the wonderful aspects of open source, and it's been very, very easy recently to pick and choose from many, many variants. But at the same time, a lot of these components are loosely coupled and not very well integrated. And so we really want to figure out how to provide a stronger coupling between these things. The other thing is, of course, we're here at ICFP, and there's a very strange inversion going on. We build applications in this beautiful, beautiful style, and then surrounded by 15 million lines of just incredibly unsafe, often ad hoc, and definitely not kind of designed in the same compositional style code. So why is it that with such powerful abstractions in our languages, the OS is still there, it hasn't really disappeared? And this came up in particular. I was having a research conversation with Simon Peyton-Jones in Microsoft Research about 4 years ago, and we were just throwing around ideas, and I was telling him about Mirage and how we'd like to build entire operating system stacks and stuff in the same style. And one little phrase stuck with me, throughout many great phrases from Simon. And he said that, oh, well, we obviously want to see this safe TCP stack, but we don't want that in Haskell. Because obviously Haskell's got to solve other problems. It can't focus on everything else at the same time. But it struck me that it should be possible for someone to build an experimental TCP stack and have the entire global community of Haskell or Camel users just take advantage of it, because we should be able to abstract the details of the OS in such a way these components just slot in as naturally as other components in the ecosystem do as well. So it's interesting that we have this barrier set up between systems programs and the way that we build other compositional abstractions toward the rest of the stack. So luckily, of course, this talk is not just a rant. We've actually built a real system that addresses many, many of these problems. And so as of a few minutes ago, I'm hosting this on this little ARM device here, which the last talk I gave, I unplugged it by mistake while showing it, so I'm not going to do that this time. And it's a standalone 1 megabyte kernel that contains the entire set of device drivers, TCP stack, web logic, and everything to serve this content. And it's about a megabyte in size. That's including debugging symbols and so on. We've gotten it down to less than 100 kilobytes in the past. And the application logic is high-level ML source code. And it's written independently of OS dependencies, and it runs on both the public cloud, the Dexter Open Mirage is running on Amazon EC2, and also on this little ARM device here as well. And one of the little cool things I'll talk to you about just towards the end of the talk is that the actual outputs of the system are small enough to track our entire operating system in Git as well. So it's not just a source code anymore, we're version controlling everything to keep track of what's going on. And just in case I disconnected last time, so just to show you if you can't see it from the back. So how many people here have used the cloud, something like Amazon or Zen and so on? So we have a fair number, we have a number of Google employees and Amazon employees here as well at ICFP. And the real problem here is just how our stacks that we're deploying for mission critical systems throughout the world are just leaning over and failing to meet their requirements as secure bits of infrastructure. And the reason for this is just, as I said, complicated configuration management, a lot of inefficiency for many layers throughout the world, throughout the time they've been built, and also long boot times and therefore a large attack surface. So Docker is one technology that has been very popular recently. And the idea behind Docker is that we're going to fix our dependency problem by taking a massive shipping container and dropping all of our dependencies into that shipping container. So the idea here is that if you have a stack of a kernel and your application and your configuration files and so on, what Docker does is that it takes the entire set of dependencies and it shoves it into a nice container that keeps track of everything. But then the thing you're deploying, in the end, is still a large collection of abstractions that have to be pulled together. So in other words, Docker has added another layer of abstraction onto the other layers of abstraction we add every 10 years or so. For example, I used to work in the Zen hypervisor, and that is another layer we added in 2002. And before that, you have language runtimes and so on. So it's obvious that it's just not a sustainable path to keep doing this. So what we want to do, and what I'll describe in this talk, is how we can just do things a little bit differently. We're going to start by breaking up this 15 million lines of monolithic operating system functionality into small modular libraries. We're only going to link the functionality that your one application needs. There's going to be no extraneous functionality there whatsoever. And we're also going to use this to build a sustainable future for how we target platforms that haven't actually shown up yet. So in addition to targeting just one platform, I want to make my functional application logic so abstract and so portable that it will run on platforms we haven't even envisioned yet. In my case, that's JavaScript, because I just don't understand the web, but we're using that as a very exotic platform that has very bizarre semantics. So this approach is something we're calling UniKernels. So we want to create these virtual machine images similar to the one you just saw through Docker, but they're highly specialized, leveraging compile time technology. And in addition to just seeing your normal application source code, they see system libraries and configuration as well. So we should be able to partially evaluate absolutely everything we know about an operating system before deploying it to a very hostile cloud network with lots of people attacking it and trying to take it apart. And in return, we're going to see some significant benefits. We have these very self-contained, tiny little binaries. They're compact, they have the minimum attack surface, they have incredible boot times, and they're so efficient we can fit tens of thousands of them into one of these little ARM boards here, or hundreds of thousands into big x86 systems. So the reward is hopefully worth the effort that we're putting into rewriting our entire application stack. So it hasn't escaped my loop, so I wanted to just tell you what the general approach is. So previously we saw that Docker just shoves everything into a large stack, and Mirage, which is the application, the operating system I'm about to explain to you, takes a different approach. It takes all of the data that it can see, and it compiles it down into a tiny little UniKernel that consists of just a minimal amount of runtime code and application code required to boot on a hypervisor. Now, I'm assuming that many of you here are not kernel hackers. How many kernel hackers do we have? Just so I know. Great, so I assume everyone here knows a bit of Haskell. So we have one kernel hacker, I'm very glad you're here, and we have about 100 Haskell hackers, so we want to make sure that you can continue using the tool chains that you're used to using. We don't want to force people to learn the baroque world of systems programming just to benefit from UniKernels. So what we're going to do is in Mirage, we're going to develop our logic using Unix, and then we're going to test it using functional synthesis to just put it into a virtual environment where you can put in all kinds of distributed system stress cases, still in Unix, and then we're going to specialize it just with the recompilation to end up running on Zen. And so throughout this, your entire workflow, you can still develop in your Mac or your Linux box or your Windows box, but the deployment procedure is targeting all of these exotic systems. And the final result is interesting. So the final specialization is so specialized that there is nothing left of Linux anymore. In fact, what happens is that the final UniKernel is running in a single address space. So this means that it's an operating system designed only to run the language runtime involved. And that address space, for anyone familiar with the normal page table layouts in Linux or Zen, is so specialized that it has specific areas just for the language runtime run at the bottom of memory, and also a specific area for foreign data to come in as well. So this kind of setup implies that this UniKernel is capable of doing nothing than running this one particular application at the end of the day, and that all data coming in from the outside world is tracked, kept at arm's length, in addition to type safety, is enforced through single address space benefits. So the end result, so I wanted to give you an idea of the benefits before I dove into the technical details of all of this stuff. And because these UniKernels are so small, I mentioned that the presentation is running off something that's about 1 megabyte in size. They're compact enough to boot and be serving network traffic in real time. So in terms of size, all of the Mirage infrastructure is self-hosting, so we have a DNS server, a web server, OpenFlow, for those of you who know software-defined networking, you might have seen Cole's talk at ICFP. And just a standard build using your Camel toolchain is about 0.5 megabyte in size. And then we just do a little bit of very simple compiler optimizations. We just did intra-module dead code elimination, and we ended up around the 100 kilobyte mark. And you can see that if you just keep going, we just did a bit less inlining and a bit more of the traditional compiler optimizations, we'd quickly fall below the 100 kilobyte mark. And these are fully type-safe kernels running on the net, serving traffic that are fully RFC compliant. But in addition to that, they can boot in real time. And so this graph here shows, with increasing memory size, it shows you how in just, so this is Linux running as optimally booting as we could possibly get it, no user space. Normally Linux takes a few seconds to boot, and this is us trying to get it as close to Mirage as possible. But Mirage itself was so fast that when we booted it on Amazon, the tool stack assumed it had crashed, and it terminated the entire connection. We had to go and phone Amazon and convince them that in fact we were in fact booting in 10 milliseconds. And 10 milliseconds is well within a TCP response time. So because you're in a TCP response time, these ARM boards, now running in my home, can actually respond to connection requests. And in the time it takes for me to open up a connection, I could have booted a VM, have it responding, and shut itself down, and all running in just a few megabytes of memory. So it gives you a sense of how we're taking the normal cloud, which is very, very large, chunky virtual machines, and making it highly elastic. So we call these things dust clouds, just tiny, tiny little particles that are booting up and just going and serving traffic on the World Wide Web. And to give you a bit of background, the reason we're doing this is because we also have a problem. So it's always nice to have a goal when you're building something as long-term as Mirage is. So one of the systems I've worked on for many years is Zen, which runs a very large proportion of the public cloud, so Amazon and Rackspace and so on. And the key question is, well, if you're building Zen to secure other people's virtual machines, some estimates say there's over 1 billion virtual machines out there now, how on earth do we secure Zen itself? And so the answer is that we need to get rid of Linux from the critical path of Zen management and use technologies like Mirage to make it simpler to manage the actual hypervisor platform itself that does not have the luxury of being virtualizable at the same time. And so this is very much trying to break down these big components into a distributed system that all interoperate very, very seamlessly. And so to give you an idea, Zen, it's a complete distribution of the Zen hypervisor. It's deployed very widely, and the software stack has around 250,000 lines of OCaml code, which OCaml being fairly succinct like Haskell, expands out to a lot of functionality. And there's an ICFP experience report for 2010, and the project is of course alive and well since then, which explains some of the components there as well. But the background here is that we're actually deploying Mirage for real into these real-world tool stacks. So it's not just an academic exercise. Now, it hasn't escaped my attention. I'm actually not at the ML workshop. And so what I wanted to figure out, and actually just have a conversation here as well, is to continue a long-running conversation I've been having with Adam Wick at Galois, who's written a very similar system called the HAL VM in Haskell. And so we have a great relationship. We're always putting each other down, and the joke is that it's like a buddy cop movie where you turn around and punch PHP in the face because you're arguing all the time, but then it really comes down to cooperating and trying to figure out how we can get the whole world moved onto a much, much better tool chain than a very, very buggy, semantically unsound stack such as PHP. So, but then what we were figuring out is that there's a lot of bits of Haskell and OCaml that obviously have a very common ancestry. And a lot of them aren't material to building systems. So for example, strictness and laziness, we can do we're not lazy by default in OCaml, but we can write lazy code. And similarly, references and purity, well, we can write pure code in OCaml too, it's just harder to enforce with the type system. But the real essence of building large-scale systems is actually down to modularity, how you build composable abstractions in something like Haskell versus OCaml. And so I thought in this talk, I would explain to you how we're using a very explicit module language, the ML module language, to build our large-scale abstractions instead of using the type class style abstractions that the HAL-VM would use. Before I get started with this, a bit of a terminology alert. I saw a lot of blank faces when talking about applicative and functors in the ML workshop, and this is because we use the same words with completely different meanings in the land of ML. So in functor, in Haskell, I hope you're familiar that a functor is a type class that lets you map functions over the parameterized type using fmap. In Haskell, in OCaml, it's a very similar concept, except that a functor actually operates over modules, and modules are a collection of functions and types instead of just a single type. And so an OCaml functor can be thought about as a module that's parameterized across other modules. Now, it's important to realize that OCaml is actually more than one language. It's actually about 2.5 languages. And one of them is a core language, which is the little ML core that you're probably familiar with and see little snippets of. But it's also got a completely separate, and Zeveloa in his fantastic 2000 paper showed that the module system is in fact independent from the core ML language. So we have another language which is used without any type inference, and it's a very, very explicit mechanism of describing abstractions and parameterizing across them. And so this module language is key to building a lot of the abstractions in Mirage, and that's what I'm going to talk about. So from an ML perspective, now that we've said we're going to talk about modules and functors, what is this thing? So we have just a few files. Mirage itself is actually just 1 or 2 files at its core, and they're not even that big. That's why we call it Mirage. The idea is it just disappears into the background once the abstractions make sense. And so it's a collection of module types. And these module types are just signatures that describe the structural parts of operating systems. So a device driver, an HTTP stack, anything that is a component in an operating system is defined through a module type. And I'll show you several examples of how these compose together shortly. And then in addition to module types, we just have these independent libraries. We have hundreds of these little libraries that implement portions of the module types. And this is why only the libraries the application needs are actually linked at the final stage. And we use functors to model dependencies between these libraries and components. Sometimes you need to build a component that needs to have a network stack or needs to have a storage system, and we just abstract using these parameterized modules to give us the capability to have a storage system without specifying exactly which one it is at the same time. And these functors are, the parameterized signatures are actually the module types we described above. So we just have module types, some libraries, and then functors model dependencies across these things. And so just to give you a sense of the workflow I wanted to give developers, this is actually how you build this website using Mirage. In Unix, I would just do Mirage configure, a configuration file under Unix. I would then compile and debug it, just like a normal ML program on Unix with all of my tools. I just cd, I make dependent, I make build. Once it's debugged, I just have to do Mirage configure --, and that just figures out the new strategy for building the operating system, and nothing else needs to change. It just needs a partial recompilation to bring in the new Zen dependencies. And all of the magic happens here via the OCaml module system. There's no cross-compilation, there's no separate routes. It really is as simple as just using your day-to-day development tools to build these microkernels. And this is essential because we're deploying this in a real-world setting where engineers who don't care about the details of this stuff just want to get on with their job and have the results running as kernels. So let me talk to you about module types, just to give you a sense of what's involved in building this system. So the first thing we're going to start with is a device driver. Now, it's pretty obvious when you're building an operating system, you're going to have a ton of device drivers. But it's even hard to define what a device driver is, because the first, most obvious ones are things like network cards and things like the low-level hardware components. But then you also have higher-level things like HTTP clients and all kinds of notions that just have to satisfy this one signature. And the signature just is very abstract. It says, we're going to have some IO monad that's called alpha IO. It's going to have some state, some type T, and it's going to have an identifier that tells you which one to connect to. And then you just have a few functions that let you retrieve the ID, given the state, connect to it, and either get an error back or disconnect. Now, this is the first bit of ML I'm showing, so just to make the syntax clear, the val defines function signatures in ML, so, and the arrows represent function applications. So the connect function, for example, accepts an ID, and because the final return value is not an argument, obviously, that represents the value of the function. And the error and the OK are known as polymorphic variants. They're just like algebraic data types, except they're extensible because they're polymorphic. The details don't matter too much for the purposes of this.
What is plus quote A?
Oh, that is, so the plus is just signifying covariance, and it's not really material to this. It will work pretty well if you just eliminate the plus. The alpha is signifying that it's an IO monad over some parameterized type. So that could be, so for instance here, we have
so
this return value that will...
So A is a type variable.
A is a type variable.
And the quote?
And the which one, sorry?
The single quote. Well, that just says here comes the type variable.
Oh, yeah, here comes the type variable. Yeah. You can ignore the plus. That's just signifying covariance, and this is just saying it's a type variable across IO. So this is a cooperative threading library that says that whenever you evaluate the IO monad, it will give you back this result, or unit in this case, which is a null type in OCaml. Does that make sense?
Yes.
Perfect. So now that we have these, we can actually build more flows. So for example, in this case, this is signifying I/O flows. I/O is obviously a very, very important part of an operating system. And all we're doing now is just simply using the similar kind of I/O monad that we defined before, but also saying we need some abstract notion of a buffer and some abstract notion of a flow that represents a concrete thing that we can read and write from. And then we have read and write functions that should still be pretty familiar. They just let you perform operations over the system. So this is great. We've now defined an abstract notion of device drivers and an abstract notion of flows. So why don't we just step up a little bit to TCP/IP? So when we get to TCP/IP, well, the stack has to be initialized. It needs to have some state. So first of all, we define a few more abstract types. We have a buffer, which is familiar from the flow, but we also need to have a notion of the IP stack underneath TCP. So we define an abstract type, IPv4. And now is where the ML module system gets interesting. We can simply include the previous device definition, and we can just do a few type substitutions to signify that the abstract type ID that was in the old device type, so this ID had an abstract type, is now just substituted in, and it inherits the type of IPv4. So whatever this abstract type IPv4 has, we've just made a connection. And we're also saying that this TCP/IP stack not only is a device, but it also exposes these flow values. So therefore, we can also do some more equivalences by saying that whatever IO monad the device uses is also the one that the flow signature will use, and similarly with buffers and flows. So we're composing these together in such a way that we're building a higher level module by including fragments of other modules and applying these type equivalences just to show that the entire system is fusing together, and anything that satisfies this type will have the same underlying types exposed in the implementation. For those familiar with standard ML, this destructive substitution here reassigns the type, so it avoids a classic problem in ML of known as a diamond problem, but we can take that one offline if anyone has any questions about how that works. Now the thing is, these module types were incredibly useful in defining a bigger system, and part of the reason for this is that we're building some very security critical components. So if later on today at the Camel workshop, I think in a couple of hours, we're going to talk about how we built a secure TLS stack using MIRAGE. So all the way end to end, it's using type-safe code and often higher level safety invariants from new features in Camel such as GADTs to ensure that we are building as secure a stack as possible. But at the very low level, there's some very, very subtle invariants that are hard to use. So a lot of security problems on the internet these days are down to things like how do you gather entropy from the system. And when you look at the Linux APIs and the BSD APIs, they're importable and they're very hard to express in a succinct way. And so I just wanted to highlight that in Mirage Live, we've just used some features that you often take for granted, things like higher order functions and so on, just to provide the same kind of functionality and map them to all the more complicated abstractions of Linux and so on. So I don't have time to go into the details, but the presentation links to a lot of the source code that shows you how just a seemingly trivial looking function, if just well designed, can map to a bunch of very, very complex underlying OS abstractions, and also give us the ability to build our new clean slate abstractions without having to worry about all the legacy. So it has been a very, very nice way to wrap these things up. But then everything I showed you is very abstract. And of course, at some point, you have to start taking decisions about the implementations that go behind these modules. And so the modules also support refinement. So I can simply I can define a new module. This is called LWT, which stands for lightweight threads. And I can just take the old module types and start giving concrete libraries that implement the same functionality that we've just defined in an abstract way. So LWT, for example, here signifies that we're using a corporately threaded library. It's a monadic concurrency library. And our buffers are represented by concrete C structs, which are zero-copy buffers that give us nice high-performance access to the low levels. And we've done similar things all the way down. So if we need, at a system level, a page-line buffer, well, we have a library called IOPage, and it guarantees that these have the right memory there. Similarly, MAC addresses are expressed through a MAC address library, and so on and so forth. So we've retained the ability to provide these nice abstract signatures, but also because our implementation has certain demands, we have certain low-level libraries that have one implementation, we can refine them down and not mix up these two concerns. So modules give us a language in which to provide this refinement. So once all that's done, we now have a series of module types. So if you browse through the Mirage types, there's around 40 or 50 little components that provide these module types. And in order to build the actual implementations, we use functors. And if you've read a paper called from CMU called the FoxNet paper from the late 90s, what they did was build a full network stack in standard ML. And this is actually one of the papers that inspired a lot of this work, because FoxNet was a little bit ahead of its time and never really saw the adoption required to push this kind of systems construction mechanism. So what we did was, instead of just building a network stack, we've built functors for the whole operating system, and we've re-implemented TCP/IP and device drivers all the way up to TLS and HTTP in OCaml. And this actually proved to be a very flexible approach. So I was just saying yesterday at my workshop that I bought a new set of speakers in my house, these Sonos speakers. And if you've ever bought a Sonos speaker, the first thing you want to do is to hack it to play the music you want, whenever you walk into a room or something. And then just to look at the protocol revealed that it runs this bizarre mishmash of UPnP running over UDP that does some firewall punching and eventually tunnels an HTTP-like packet across this kind of monstrosity of a network stack. But I still wanted to play my music, so it turns out just by repurposing some of the Mirage network stacks, I could just take the UDP code, just take my HTTP stack, mash them together, and just do a bit of typing improvements. I ended up being able to play music at home by taking components that weren't really designed for it and applying them the right way and ending up with something that could communicate with these speakers. Previously, I would have had to cut and paste kernel code in order to get the right bits of stack and so on. And it's been lovely just to be able to use Mirage for solving these kind of communications problems in these very, very kind of ad hoc devices that come together. And also, in these implementations, we have many, many different implementations. So in addition to satisfying the network stack signatures through Unix sockets, we can also just swap in Zen microkernels, JavaScript, FreeBSD kernel modules, and so on. So how does this actually work? A Mirage component, something that's trying to satisfy these module types that I just described, is parameterized by functors. What does that mean and what does that look like? Well, it's very straightforward. If you just ignore the first line for the moment, this here represents fairly normal ML code. We're saying that I want to start something and I want to give it a console, a file system, and some HTTP server. Then I will define a callback, and the callback will just log saying that it's starting. I will parse the URI, and I will dispatch that into my HTTP server. And then eventually, I will take these higher order functions and I'll apply them to this HTTP server that I started, and off we go. So this is actually a fairly standard stack. If you're doing this normally, though, we would have had to have a global module defining the HTTP module. But what we have here at the top line is we've actually parameterized our entire stack by saying that this main function will have some console, some key value stored that's read-only, and some HTTP server. And that everything else in here uses these modules and these signatures. And that's really all it takes to lift your dependencies into this functorial world. You just explicitly say what components you need, and then everything else follows from there. So why would we care about this? Well, this is because we want to configure this website in many, many different ways. So if I take this web server I just described, it's got my homepage, for example, the HTTP and so on. Then the first thing it does is that it needs an HTTP implementation. And the traditional way, for example, if you're using Yesod or one of the Haskell stacks, would be that it would bind to the kernel and it would give you TCP sockets through Unix. And eventually, you have a dependency on this 15 million lines of kernel code. Remember, our goal is to test the server using this, but to wean ourselves off the kernel code. So how do we do that? Well, the first thing is don't try to do it all at once. So we've got this OCaml network stack, and what I want to do is I want to say, well, from the HTTP stack, instead of just using sockets, would you mind giving me an Ethernet device from Unix instead? And this Ethernet device simply gives me raw network frames. It's using the TUNTAP interface for those of you who've played with this. And what we can now do is we can hook in our OCaml network stack, and with the same HTTP implementation, the same library, we can start shimming in packets from raw Unix and start taking over a portion of the kernel operations in user space. But we haven't yet quite leaped into the Zen mode. So we can use all of the usual debugging functions to debug the network stack. Because we didn't have a formal specification of TCP, the network stack did have bugs in the early days. Although Peter Sewell is now helping us with formalizing these things. As always, the formalization seems to happen after the hacking. Some things never change. But later on, we're happy with our network stack. The UniKernel stack is not perfect. It's serving these slides successfully. And we want to get rid of all of the other components, such as device drivers and so on. So at this point, it turns out that our only real dependency in Unix for a web server is, in fact, this Ethernet stack. So we've been pulling in millions of lines of code just to serve network traffic. So we just provide an equivalent module in Zen that implements this network interface, except that behind the scenes, it's got a chain of abstractions that implement all of the underlying device drivers and so on required for Zen behind the scenes. But you as a programmer just don't care. This network stack satisfies an Ethernet signature, which in turn satisfies a TCP signature, which in turn satisfies an HTTP signature, which in turn stores my application. So we've successfully built a chain through this of abstractions without having to actually worry about all of the details. Our system provides those abstractions for you. So I hope that gives you a sense of how we form these module chains in order to form our actual systems. So obviously, building functors is no trivial task because it took some time to define these module types and so on. But we have satisfied our important property that we'll have no operating system dependencies in the usual code that we write in ML. And we've avoided the need for C stubs and all of the things that you normally see pervading code when it needs to interact with the system, just by abstracting over it using modules. And then the other thing we provide is that obviously not all of the UniKernel community has shifted over to using Mirage, thankfully. That would be a few too many people to deal with. But what we do is we take a lot of the code that we've built and we provide Unix equivalents. So we've had a lot of debugging help from the UniKernel community who are using my web stack, for example, but without having to see any Mirage involved at all, because we provide libraries where we apply these functors using just normal Unix libraries, and then they're suitable for interactive use. So without really knowing it, a large part of the UniKernel community has been helping us debug our core logic just by using these kind of interactive modules for their own purposes, which are not Mirage related. And so it's been a very successful way of separating these dependencies. Unfortunately though, well, I painted a very rosy picture. I say that they've been using it, but in fact, when they find a bug and they come to start debugging it, these functors are very heavyweight constructs. You have to, as you noticed, factorize all of your code that was previously written at the top level across these module types. And they need to be applied in some concrete combination to actually form that one of those backends. So you saw, for example, all of the modules that went into building the Zen stack, and you wouldn't have to want to do that manually. That would be very, very painful. So I mentioned that the UniKernel module system is in fact two languages. So the UniKernel language is two languages, a module system and a host language. So the obvious answer here is, why can't we manipulate this much more limited language, the module language, inside our host language? And it entered the EDSL. And so what we did was we just said we want to provide the ability to manipulate all these module stacks. And so why don't we just manipulate them in the host language and then metaprogram our way by generating code that actually translates into module applications. And so this EDSL is extremely simple. I'll just describe how it works, but it'll actually be familiar to many of you who've done dynamic types before. We simply have to, in our host language UniKernel, we define this abstract. Now this is going to be slightly hard to explain verbally because we have a type. So let me call it tip, perhaps. This represents the type of values that represent module types. So this could, for example, be a network or a TCP for signature, any of the signatures I showed you before. And we create a combinator here, this at arrow, that says given a type and a second type, just form an application of those types. So this represents functor application. So if I was parameterized over a console and a file system, I would apply the file system and, well, in this case, an IP stack, and result in a final signature. So this represents functor applications in the host language. And we use this to manipulate all of our types. But then we also have values. We have the concrete Zen or Unix backends that we want to do. And so we also define a type of module implementations. So these are some values that represent concrete module implementations. And we also have this combinator called $, which applies implementations. So this is the reverse of the previous combinator. All we say is that when given an alpha to beta implementation, and given an alpha, we'll apply it and will result in an applied module at the end of the day. And these two are example functions, foreign and type, that just provide entry points into the types that we've just described. So with these, we can actually build all of the configuration, all of the policy around how you assemble these applications in pure ML. So, for example, this website, I need to say that I would like to create an environment variable called net in order to decide which network stack to provide a socket binding or a network binding. And then I will have lots of other policy and interactive dialogues or whatever to provide the configuration. At the end of the day, though, I will say I need to construct a network stack that I can provide my website, and given a console for logging, we'll figure out based on the host policy, network and DHCP, and just run these functions that will run the EDSL that will provide me with the right combination. At the end of the day, the type of this entire function, it looks very complicated. The implementation is extremely simple. It says, given an implementation of a console, give me back an implementation of a stack. What does this look like when you apply? Well, here we're constructing an HTTP server. So these conduits are abstract notions of sockets. And then here we're saying, give me an HTTP server binding to TCP on port 80. And then we're saying here that our web server that we just saw is of type console. It needs to have a storage system, a key value store, and it needs to have a web server, and then it will result in a job, an executable MIRAGE job. These are all just types. And then all we have to do is apply this against concrete implementations. So we have a default console, which is just a normal, standard out console. But if you're building a production system, you would redirect this to some kind of persistent log. We have a real file system. I haven't shown that in the example here, in a real server that we've just constructed up here. And the server represents a concrete mechanism, a concrete strategy for building the abstract HTTP server. So this EDSL this is the little fragment I showed you, maps precisely to the module types we parameterize our application across. So here we see console to KVRO to HTTP to job. Here we see console to KVRO to HTTP. This is a concrete HTTP server interface, and it results in a job interface which has a start and a stop. So there's a nice duality between our EDSL and the actual module language that we've defined. So what actually happens, what code gets generated? Well, it's pretty straightforward. When we're developing in Unix, this EDSL evaluates through a series of module applications. So in this case, we're developing in Unix. So I'll say, given this socket stack in Unix, and given a console, construct me a stack. Then you can see that given the stack, construct me a conduit, which is a network channel. And then given a conduit, construct me HTTP. And before you know it, you've built an executable version through the EDSL of your application. This is all automatically done behind the scenes. But it's actually quite readable. So if you need to go through the module chains to figure out what's going on, which is important for debugging, it's pretty straightforward. There's no real magic hidden there. When you switch to Zen, the modular assembly gets much more elaborate because you can't just bind to Unix. You need to bind to a full module stack of implementations. So all of a sudden, our network stack becomes an Ethernet interface that we've seen here, which we get from a network interface. And then the Ethernet interface E is bound to IP. Then we bind from the same IP interface two things, UDP and TCP. UDP is pretty simple because it's a simple protocol. TCP requires some notion of a clock, some notion of entropy, so you can do timers and initial sequence numbers. And then finally, we take all of these things, and this epic functor application happens called the stack, which just applies it. You never need to see this. Let me re-emphasize this again. But behind the scenes, there is a principled approach to modular construction that is just happening on your behalf. And then you take the results of the stack, and we have exactly the same flow of module applications that we had earlier. So it's a very, very explicit way of providing things. There's very little type level magic going on here. We just provided the policy languages in EDSL to let the programmer construct these in a nice, safe way. Then everything just runs. And we've met our goal, which is good news at the end of all this modular code. This slide deck I presented to you, it can be built as a Zen UniKernel. But because I don't want to have a file system, when I was presenting this in the ARM, I didn't want to have to deal with storage. So all of the data, all of the images and the text here has been built directly into the image. We just converted our file system into an OCaml module that had all the data built in. We can also read it dynamically from disk if you want to, for the bigger websites. I've tested this, and I can run it in all these different combinations. So it really does give you just well-typed rope to hang yourself with. You can choose many combinations of modular assemblies, and you can build nonsensical systems, but at least they're well-typed. You know exactly what the behavior of each one of these things are at any given time. And crucially, we don't know the environments these things are going to be deployed in, so we wanted to provide the flexibility to make it possible to pull this off. So just a few little details, the reasons why we don't want to use a module system. So again, Haskell does a great job of error messages. OCaml is getting better, but it's certainly not quite as helpful often in the module system when it comes to turning modular level error messages into human readable values. And most often what happens is that when you have a bad modular application, you get about a megabyte of signatures dumped to your console, and they tell you there's a difference in there somewhere. So with our EDSL, small type mismatches turn into very understandable type mismatches in the host language. It just tells you this console is not a type implementation, and you have to go find one there. And we can also use all of the nice things, all the optional arguments, and all of the features of the host core ML language, your type inputs and so on, tab completion, editor integration, and so on, to just manipulate our policy language. So for example, in the case of building a TCP stack, we can use optional arguments to say, most of the time, I don't want to provide a custom clock or a custom entropy. Just give me back a sensible value. And optional arguments provide a great way to pull that off. In the module language, you have to be extremely explicit. You can't just leave modules out. Whereas an EDSL can take policy decisions, apply the right ones, and let you get on with your job of actually creating systems. So it's a nice way to manipulate the host language. So I won't go into too much detail with EDSL, but one of the good things is that by building an EDSL, we can actually extend the notion of device drivers extremely easily inside Mirage. So someone else came up with, in fact, our TLS stack was built by two community volunteers who, one of them finished his PhD, went to a beach in Morocco to hang out, saw a blog post from Mirage, and decided to start hacking in a TLS stack. And the first question that they asked while on this beach in Merleft, I think in Morocco, was how do we get entropy? And so the entropy device was just added by constructing an abstract type and a module type, the module type I showed you earlier, and then defining a first-class module. So in OCaml, all of the modules and functions I described can be passed around as values. And so we just have to say that any implementation just defines a module type and then some abstract mechanism of configuring that module type. And then by doing this, you have everything you need to construct implementations, and it's a very, very straightforward addition to the language. So this extensibility lets us manipulate future modules in a polymorphic way without worrying about their exact details. So it's just like dynamics. If you've played with dynamic type systems, then dynamics are always a pair between some value and a value that represents type. All we've done here is to lift the conversation from just instead of a single value to some type that represents a module type, which is a collection of abstractions, then a configurable and a constructional function that will let you apply and that module in a functorial sense. So really, we're just heading back towards manipulating modules as first-class values, and then we can just use them very, very simply. And we use GADTs in OCaml to ensure that whenever you are trying to apply a module implementation to a type, any application that would be unsound in the functor language is also unsound in the EDSL. So we just don't have to worry about signature level errors and so on, even though other people are studying our systems. The details of this are very ML centric, so I just wanted to give you a sense of where the abstractions lie without going too much into the details. So I hope I've given you a sense of what modular programming is like. It's much more explicit than the typical Haskell abstractions. I did spend some time in the last few weeks trying to figure out how to implement some of this stuff using type classes and associated type families, and I must admit I got a little bit lost in some of the details of trying to implement functors. Then I ran across the backpack papers, and it turns out this is a really, really interesting ongoing topic in the community right now. So I thought this would be a great time to just bring this conversation about explicit, simple modularity, which comes with its own syntactic drawbacks and its own unique class of complexity, but it has proven to be a very, very viable way of building these large-scale systems. And the secret here is just to split the problem into two chunks. Use metaprogramming to manipulate these things in an EDSL, and then just eliminate this entire stage in the next stage of programming and end up with a simpler system. So we are going away from building very, very complex type systems to building stage types that do code generation that also help a lot with debugging and so on at the end of the day. And all of the flexibility and so on has really panned out when building these things in real life. So I promised a little bit of a bigger picture at the end of it as well. What are we using Mirage for? So it's been going for a long time, and it's actually got users now as well. So the first thing we do is we track all of our deployments, and this has been a revolutionary way of just keeping track of what is going on in the cloud. So normally we track all of our source code at GitHub or Mercurial, on Bitbucket, whatever service it is. The way that we work in Mirage is that all of our source code updates just go to a normal website. So this is the Mirage website, with all of the usual templates and so on, markdown files representing the code. But every time we actually do something, it's automatically built. Now I can't quite, let me just go to pull requests. The website is automatically built using a website called Travis. So what happens is that every time someone sends us a pull request, we rebuild the entire website using a continuous integration system. So this system is from scratch, rebuilding the entire operating system. I'm obviously not going to show this in too much detail, but it's just going through and doing a from scratch rebuild of the entire system. And then Travis can also deploy the system, the resulting kernel, into another Git repository because they're so small. So on GitHub, the result of this build is sent to a deployment repository. And this deployment repository, I will just click here, represents every single UniKernel ever built. Let me just go there, there we go. So what we have here is a Merkle tree that is a hash of hashes representing every single commit that ever went into this UniKernel and its configuration policy represented as a hash. So if you ever need to reconstruct it and go back through our Git trees to find out where did this deployed system come from, well, we have one configuration file that says this is the IP address of the host as it was deployed. And then we have the actual kernel itself, which, including all of the data, everything that goes into the live Mirage website, was 3 megs. And this includes your images and so on. We haven't particularly tried to optimize this thing. So this workflow is interesting when you're dealing with the cloud. It becomes amazing when you're dealing with ARM devices, because we can now do firmware deployments across multiple houses and so on and so forth, thousands of people, and just ask them to git pull. So we can, in a principled way, no matter how long they've been disconnected, just bring the whole thing back into a version controlled world. So this unification of UniKernels, of source code management and binary management is interesting. We've got tons of code around this right now, and we're still understanding the implications, but it's just changing the way that we work. And the reason for this is that we've actually been learning in the last 5 or 10 years exactly how to deal with large code bases using version control tools. So a lot of you probably use git tag to link to tag specific revisions. Well, we can git tag our deployments. You probably use git log to figure out what's going on in your source code. We can just git log everything that was ever pushed to the cloud and find out exactly what's been going on. And because it's a Merkle tree based deployment, it's very hard to forge new commits. It's very hard to change things because they depend on a hash of the previous names. And most awesomely, we can git bisect, which is that it will do a binary search all the way back to previous revisions, trying to figure out exactly when a bug happened. But it doesn't just do this from source code. It goes back, rebuilds all the UniKernels, and then with one script, it can tell you exactly which binary caused this one problem in a reasonable human doable amount of time. The second thing is just low latency deployment of security updates. So I mentioned to you the UniKernels boot very fast. All we have to do now is to do a git pull, and our UniKernels can watch their source code trees immediately. So they can just say, well, I'm going to watch the security branch of co-HTTP, the HTTP server, and just rebuild myself whenever something happens in Git. So instead of waiting for binary upstream packages to go through a long chain of pushing things out to me, I can just watch the source code that went into myself, and I could link the OCaml compiler into a UniKernel or into a helper VM and just rebuild everything. So it becomes a very, very straightforward way of just tracking things and closing the open source loop, if you will, at the same time. And of course, remember that everything we're deploying is also fully statically type-checked all the way down to the device drivers. So we're already immune to a basic class of attacks, and we're lifting the conversation up to the more sophisticated attacks. But of course, right now, when we deploy services, we're still dealing with the 1980s buffer overloads attack and dealing with complex policies with ad hoc configuration languages and all kinds of crazy complexity. So this is really saying it's not perfect, but it's just trying to give us a manageable problem that we can actually have a chance of solving in the next few years. And it's also quite nice that we no longer need to have a PC to do much of this development. So a chap called Andy Ray from the Mirage community built a full, along with Jerome Valoum, who built a JavaScript compiler OCaml, and Facebook, who will hopefully open source some of their code soon, have been working on this incredible set of JavaScript tools for OCaml. So we can now build ARM kernels purely from JavaScript. So the OCaml compiler is a self-compiled JavaScript. John Donovan from Citrix got the linking toolchain built using Scripted. So just from my iPad, I can build a UniKernel and have it pushed to GitHub, and then have it deployed on my ARM without a PC ever being involved. So it's just bizarre how all of these tools and all of this compilation toolchain have just come together to form a very, very effective way of just deploying UniKernels from any IDE. And of course, in the future, as UniKernels emerge for other languages, like F#, for example, you should be able to use the full set of Visual Studio tools, for example, to have the same kind of benefits. We're just using a very Unix-centric approach, which is why OCaml's our favorite language for this. But it's entirely possible to use other systems. One of the lessons we learned as well, I heard lots of chatter about Cabal, so I thought I'd give you a sense of how we do source code management in Mirage as well, and OCaml more broadly. Any library OS like this involves over 100 libraries and a ton of deployments, and of course more and more people just contributing packages as we go along. So one of the things we learned from Cabal, I had some great conversations with Brian O'Sullivan and Johan and many, many others about what Cabal perhaps did less optimally than it should have been learned from a huge growth. And we eliminated upper bounds in packages, and we ensure that any new packages that we pull in are admitted by continuous integration. So this makes it much, much easier to do development because you're not always pinned and dealing with constraints at the same time. Everything in our source management, OPAM is our source manager, is based on a distributed Git workflow. So we have a stable repository that's hosted on OCaml/OPAM repository on GitHub, but we can actually just define inside our package manager another Git tree from which to pull cutting-edge packages and form a single universe that is merged. So the Zen team, for example, that work in their very large code base, the Mirage team that is separate, and the Oxygen team working the web stack, all have these OPAM remotes that represent the cutting-edge versions of their packages. So just from my laptop, I can OPAM switch into a different compiler. I can add these remotes, and I can pull in all kinds of distributed packages with one command. So it's a very convenient way of testing and providing collections of features to people, even though you have a lot of repositories. And the other thing that's important, I think this is something that is very important, is that there's some problems like constraint solving that should not be re-implemented by package managers. So OPAM has a built-in solver that just did not scale to the number of packages that we got. And we were wonderfully lucky to have the Mancusi team, Roberto de Cosmos here at ICFP, and they just provide high-quality solvers that in very, very short amount of time solve very hard, very NP-hard problems and just give us an answer. And we're leveraging the Debian repository tools such as Africa to pull this off. So between these things, we're very happy with OPAM, and every single Mirage library is now tracked in the global OCaml package manager, and things have not yet collapsed. I just wanted to give you a sense of the growth of the community. So we've had, this is just a number of contributors. We're up to about 200, and just kind of steady growth. I'm not sure if this is a hockey stick curve or it's leveling off, and we've hit our peak with Camel. But either way, it's very, very nice to see the size of the community growing. And this is just a number of packages in the repository. So this is the number of unique packages. We track historical packages as well, so that at any point you can choose to go back in time to older revisions because they have a more compatible type signature or more bug-free, whatever it is at the same time. So overall, we're just very happy with Mirage just kind of leading the way in package management, but also the overall OCaml community also coming together to contribute a vast number of packages into the system. So it really is helping us to catch up with the wonderful work that's been done by Cabal to lead the way in this in Haskell. So I just wanted to give you a sense of where we are, and I'm just going to wrap up now. There was so much more I wanted to tell you about, but luckily we're giving a number of demos and talks at the OCaml workshop next door. I'll be around until Sunday morning. But in particular, there's components here that are blogged about extensively at openmirage.org. One of the most exciting is this Ermin library, which represents a pure OCaml implementation of Git, and it actually underlies the Git workflow I just talked about. And so we've actually just been blogging about how we used Ermin to re-architect the entire distributed stack in Zen, and use Git to debug distributed systems, because every IPC is recorded in a global graph and then dumped into a Git repository. So it's a wonderful, wonderful start of a database that is providing us with a nice library-based approach to building principled consistency algorithms and so on for building complicated systems. The OCaml TLS stack is exciting. It helps us catch up with Haskell, which has obviously had one for some time. vChan is all about shared memory communications, how we can build very high-performance functional servers. And C-types is a bit of a dark horse. It lets us bind to libraries from Mirage without having to import them into our address space. So it's such a modular library that we can actually spin up virtual machines running Linux, running OpenSSL, and treat them at arm's length for reasons that should be obvious, and use them to communicate with UniKernels. So it just provides us with the FFI abstractions that extend the library approach into this world. So all of this is online, and I'm very, very happy to talk about any of these later on. But also, I wanted to say it's extremely important sometimes to just get involved in these projects as well. So UniKernels are an amazingly fun way to just get started in OS programming and OS hacking. And nothing stresses an abstraction toolchain like an operating system, just because there's so much code involved. And so it's one thing to sit around arguing about abstractions and scalability. It's another thing just to go build it and see what happens. And so this is why Mirage OS and OCaml, HalVM and Haskell have been just a very educational process. We do have a challenge of trying to figure out how to evaluate these abstractions, because as a systems person, I need to see some graphs. How does one evaluate, the benefits of type classes or the benefits of modularity in OCaml? Well, one answer is to just build massive tool stacks and just see what they look like, and then try to start having that conversation. And we're very lucky that the team has been so cooperative in open sourcing HalVM as well. So we actually have a number of these UniKernel sites available now. There's lots of really interesting scenarios. We're going to put more of these on our website. Custom routers is our one of interest right now. And the final thing is that behind all of this, I'm still a systems person at heart, and we want to make this stuff very, very fast. So one of the nice things about building these UniKernels is that we can, in a very, very kind of controlled way, we can do performance abstractions of the cost of various language level abstractions at scale. So in OCaml, FUNCTOR application is an inline, for example, and we're looking at these kind of things. But it's nice to have these large code bases to provide us with these useful test cases. But most importantly, we talk a lot about the safety of functional programming. We just need more contributors to contribute actual rock-solid implementations of protocols. So, TLS has been done, but think of NTP, DHCP, there's tons of protocols. And once we have these in our respective package managers, it gives us a base from which to go out, talk to the wider community, and show that functional programming is a realistic way to build systems. And the only way to do that is to just push high-quality code out to package managers and maintain it in just the same way that is done in the Python, the Ruby communities, and all of the other communities that have been very, very successful at scale. We're doing a lot of this, but we need to do more. And UniKernels are just a fun excuse to do that, be it in leisure time. They just give you a nice context. But underneath it all, we just need the implementations. And the reason for this, I just wanted to show you, is that we've got a large initiative right now in the UK to build something called NIMOD, which is a mechanism of decentralizing the cloud, so we can actually run viably systems on the edge. So a lot of these Raspberry Pis and QB boards that you see here are going to be deployed into UK households, and we want to be able to do this in such a way that I can deploy this in my granny's house without her having to become a sysadmin. And the idea is these UniKernels, these version-controlled, type-safe bases provide a much, much safer foundation to build routers or gaming platforms or anything you want to deploy in a house, with the benefits of the central cloud, but without having to be tied to a big, non-resilient central system. And so Mirage ARM is going to be the foundation for this. So we're using this to build all kinds of DNS infrastructure and things. And you can find that on NIMOD. It's a new site. It's emerging, but it consists of all of these components I talked about being put together into an integrated system. And we'd love to have either comments or contributors or ideas, just anyone who wants to get involved with that as well. And so this is just a summary. There's been a lot of information thrown at you. Thank you so much for being so attentive during this talk. We're a Linux Foundation incubator project, led obviously from my group in Cambridge and Citrix. And there's lots and lots of blog posts and stuff online as well. So hopefully it provides a friendly communications forum for anyone who wants to start a conversation about type classes and modules. That's what I'm particularly keen to figure out in the next few days at ICFP. So thanks for listening, and if you have any questions, I will take them now.
This is all quite fantastic. Two questions. So if you're familiar with how applications are linked together in the TinyOS system, I was wondering if you could just briefly compare and contrast. And given the tiny image sizes, presumably Mirage kernels could be pushed into even smaller systems if you wanted to go into that kind of low-power sensor network.
They could. So from a systems construction perspective, it's very similar to TinyOS, a single address base. The key difference here is that we're putting types on top of our single address-based systems. So any system you build is a balance between security and performance and all of the other constraints that go into it. So statically typed systems provide a really nice balancing point for introducing something that you can enforce a compile time and then not have to pay the cost for it at runtime. So that's why we picked Camel in particular, because it just has a nice predictable cost model and so on. But the end result is very embedded, actually. It looks very much like TinyOS. In fact, we've had someone port to various embedded systems. So ZenARM supports a lot of these embedded systems, and there's a lot of convergence there. Now, I'm very, very keen to make sure, though, that any new system I build is fully type safe as much as possible. I just don't think it's responsible to deploy real-world systems that feature unsafe code, especially if there's so much at stake in terms of personal data and so on. And there was a second part of your question, sorry.
Oh, yeah, so the second one is very small. So it's very interesting to see how Travis and GitHub here are used as infrastructural components, not by humans, but by your automated deployment system. I looked at the GitHub repo. I noticed that it had images going back a year, but no longer. At 3 megabytes per commit, I imagine you go over GitHub limits and maybe reset periodically. But is there anything in their terms of service that is against automated usage like this?
I fully expect to get kicked off GitHub at any time. I mean, it is a bit unreasonable. I mean, this is not a statement against GitHub, but this is the reason why we're building Ermin. So Ermin is a lot like Git, except it extends the policy required. So it makes it much, much more efficient to manipulate binaries. For example, one Ermin algorithm is that it provides a rebasing window where it can leave you with the last week of commits, but everything else is rebased in real time in such a way that the applications can observe it and send off to a logging server where it's got terabytes of storage to store the big data. But anytime you clone the head of an Ermin database, it will provide you with just the last kind of week of data. So this is garbage collection done asynchronously. Crucially, it can be done asynchronously from the running system. So I can choose to garbage collect in just the way we garbage collect normal heaps, except this is a tree structured heap. It's a DAG instead of a global memory as well. So,
very cool.
Thank you.
So that was indeed very cool. I've heard it said that the big problem in the modern world is not lack of operating systems, but lack of good configuration systems. And that a lot of the problems with deployment on the web are configuration problems. Even if you go back to the old Intel arithmetic bug way back, that was a configuration issue, really. So a lot of this is actually about configuration. So A, I want you to comment on that. And B, what are the possibilities of taking your configuration techniques? And right, this is very much an OCaml only world that you're working in. The Haskell project you mentioned was Haskell only. What about using one of these languages for configuration, but then pulling everything together from